Okay, so the first question was on 19.2, Part A, and the question is, to compute the limit as x goes to infinity of f of x. In this case, f of x is 3x minus 2 over x plus 1. So the way that you do these are exactly the same way that you deal with them when they're discrete. So here I have a function that's continuous, and I'm thinking about what the long-term behavior of that function is. And it's the same technique or the same thought process that goes into dealing with a discrete population and thinking about what long-term consequences there are for discrete populations as well. Okay, so it's the exact same technique. So if you remember, that technique was we look at the denominator and we look at the highest power, right, the highest order, and we're going to multiply by 1 over x to that power. So in this case, it's just 1 over x because I have a linear denominator, right? And this is going to change the form of our equation but not the value, because I'm multiplying by something divided by itself. So I'm just multiplying by 1. So my first step is going to be to distribute 1 over x to the numerator and the denominator. And then I simplify. So here, my x's cancel, right? So I get 3. And here, my x's do not cancel. Okay, we can think about the 2 as being a 2 over 1, and we multiply numerators, multiply denominators, right? So we get or we can keep it as 2 times 1 over x. It doesn't matter. And again, our x's cancel, and we're left with 1. 1 over x. Now, we want to take the limit of this as x goes to infinity, right? So we have to think about now distributing this limit to the numerator and to the denominator and to each term. So if I take the limit of 3, that's just 3, right? 3 doesn't change depending on x. If I take the limit as x gets really large of 2 over x, what's that? 0. Again, if I take the limit of 1, let me record this. If I take the limit of 1, I'm just 1. That doesn't change. It's a constant. But if I take the limit of 1 over x, what is it? 0. Okay. So I get 3 over 1 or 3. Now, if we reflect on the answer in terms of the original function, and as you go through parts A, B, C, D, you'll start to notice that you might be able to predict some of the answers. And I can give you an explanation for why. The explanation is that the highest order term dominates the dynamics of whatever happens for rational expressions. Here you have a 3x minus 2 over an x plus 1. The numerator and denominator are of the same order. They're both linear. So they're roughly going at the same rate. Okay? The numerator is 3 times larger than the denominator. So over time, the ratio will go to 3. That's it. Done. So you can always check your answer by reasoning through it that way. If your denominator has a higher order, for example, x over x squared plus 1, then the denominator will dominate. It will grow much faster than the numerator. And what do we know about the long-term behavior of those situations? When the denominator grows really, really big relative to the numerator. Goes to 0, exactly. So we're going to get a situation where we go to 0. If your numerator dominates the dynamics, if your numerator has a higher order, like x squared over x plus 1, what do you think is going to happen then? Your numerator is getting bigger faster than your denominator. Goes to infinity, exactly. So that's the general rule, okay? So if you have, general principle, if you have then you'll have the ratio of the coefficients. So I'll just put here a to the n, b to the n. So we suppose it's some kind of polynomial, okay? Okay, and you have, as an answer, long-term dynamics, you'll have the ratio of the coefficients. So in this case, it was 3 over 1. If we had, it could be 3 over 2. It doesn't have to be an integer or a whole number. If you have some kind of nth order over nth order, so now they're different, okay? If the numerator is bigger, then we're going to go to infinity. If the denominator order is bigger, then we're going to go to 0. Okay?